Добрый день еще раз всем. Давайте продолжим пленарную секцию. Вот после кофе-брейка слегка народ собирается. Вот, подождем коллег немножко. Но пока представлю следующего докладчика, доктор технических наук, профессор Виталий Евгеньевич Захарченко, заместитель технического директора по НИОКР и ПО научно-внедренческой фирмы СМС. Доктор Виталий Захарченко, R&D Sensors, Modules and Systems, Ltd, Russia. Добрый день. Вы вживую. Все, прошу вас. Спасибо.
Можно включить презентацию? Ага, отлично. Спасибо. Давайте начнем. В отчете экспертной группы по цифровым технологиям Digital McKinsey говорится о том, что в ближайшие 12 лет нас ожидают кардинальные перемены. И более 50% рабочих профессий будут так или иначе компьютеризированы, они будут изменены под натиском цифровых технологий и новых реальностей. Именно это и является, по их мнению, признаком цифровой революции, цифровая промышленная революция 4.0, которая сейчас шагает по всему миру. Это затронет порядка 1,2 миллиарда рабочих по всему миру. Среди них будут, естественно, техники, программисты, технические писатели, актеры, сценаристы, ну и так далее, и так далее. Ну, на самом деле, по заголовкам газет можно уже видеть, что, например, программисты больше не нужны, потому что появляются различные технологии, как программирование low-code, no-code или ассистенты программирования, которые называются copilot и так далее. То же самое мы видим, что как изменяется профессия технических писателей, да, и всех, кто так или иначе занимается документацией. Сейчас появляются тоже ассистенты ввода текста, сам чат GPT, прочие GPT, Яндексы, прочие инструменты, которые позволяют чуть менее вдумчиво генерировать текст. Да? Также мы видим в новостных сайтах, что того или иного актера в фильме заменила нейросеть, он по этому поводу переживает и так далее, и так далее. То есть тренд уже начался, так или иначе цифровые технологии входят в нашу жизнь и начинают ее менять. Но я хотел бы поговорить не столько о нашей жизни, сколько о промышленности. Я представляю компанию, которая занимается автоматизацией в промышленности. И в части промышленности эти цифровые изменения не так явны и не так, скажем так, системны, как хотелось бы. Однако в России подход к цифровизации в промышленности, он обозначен как правительством, так и президентом России, сформулированы следующие цели на до 2030 года. В первую очередь это добиться безопасности и технологической независимости в промышленности, также увеличить квалификацию и компетенцию персонала, увеличить эффективность и производительность различных систем. Также особое внимание уделено созданию систем моделирования, платформ моделирования, созданию цифровых двойников и систем ведения проектов, проектирования. На наш взгляд, возможно добиться этих целей, если следовать поступательно в 4 стадии. Первый этап – это зафиксировать текущее состояние. Необходимо то состояние, которое есть на каждом из объектов промышленности, оцифровать. То есть преобразовать к цифровому виду. Нужно перевести документацию, алгоритмы, модели, схемы, те исходные коды, которые крутятся на серверах, на контроллерах. Это все нужно сохранить, описать и этим начать пользоваться. Также сюда можно отнести и технологические уставки и карты состояний. А на втором этапе это унификация и стандартизация для всех систем, которые есть на предприятии. То есть это создание общих правил для сбора данных, для управления, для отображения, для диагностики. То есть создать некий шаблон, с помощью которого будут собираться все данные, с помощью которого будут они обрабатываться и представляться на экранах корпоративных пользователей в едином унифицированном виде. То есть насос, созданный одной системой в одном конце предприятия, и насос, который создан другим предприятием в другой год на другом конце предприятия, должны на мнемосхеме выглядеть одинаково, должны быть одинаково описаны и должны иметь одинаковое мнемоническое обозначение. Также на второй стадии необходимо создать цифровой ландшафт. Здесь уже появляется типовая пирамида автоматизации. Нижний уровень должен быть это контроллеры, второй уровень это человек-машинный интерфейс или система диспетчеризации. Дальше должны появиться системы управления производством, планирования производства, ну и так далее. И дальше уже возможна оптимизация. Но на данной стадии самое главное закончить автоматизацию уровнем формирования отчетности по работе предприятия. Третий этап это мы назвали развитая автоматизация. Здесь уже речь идет о том, что необходимо подключить системы Industrial Internet of Things. У этой части есть несколько целей для внедрения. Первая из них – это собрать данные, которые необходимы для оптимизации различных процессов, которые не автоматизированы. То есть эти процессы есть, эти задачи выполняются, но так или иначе автоматизации на них нет, и необходимо эти данные собрать для того, чтобы обеспечить хоть какой-то сбор информации о неавтоматизированных задачах для того, чтобы планировать ресурсы. Вторая цель, которая может быть достигнута при планировании интернета вещей, это обеспечение межсистемного взаимодействия посредством протоколов на основе интернета вещей. То есть идея здесь следующая, что две системы, которые ничего друг о друге не знают, но знают общий транспорт, протоколы интернета вещей, могут подключиться, узнать друг о друге и понять, какие же функции есть у системы партнера, и этими функциями начать пользоваться. Следующая часть – это безопасность, информационная безопасность и защищенность. Я думаю, что здесь комментарии излишни. Все и так понимают, к чему может привести открытие систем автоматизации и прямое их подключение к сети интернет. Третья часть – это использование носимой электроники. Идея здесь достаточно проста. Сделать так, чтобы у сотрудников предприятия рабочее место было у них в кармане. Планшет, телефон или еще что-то, там, где он находится, он может в любой момент посмотреть и текущие технологические параметры, и ознакомиться с документацией, и составить план работ на ближайшее время. Следующий шаг – это создание виртуальной или дополненной реальности. Я думаю, что тоже более-менее это понятно. Создание моделей для цифровых двойников, для создания плана производства, для виртуальных испытаний, для процессов обработки данных, вычислений и оптимизации. Следующий компонент, который здесь может быть применен, это сервисы массовой разработки систем, о чем я буду подробно рассказывать чуть позже в своей презентации. Также важно на этом этапе создать системы обучения и системы тестирования для того, чтобы повышать квалификацию персонала, который обслуживает систему и выполняет управление, используя эту самую систему. Здесь же выделяются ключевые показатели, Key Performance Indicators, и более того, начинается управление по этим KPI. И последняя, но немаловажная часть, это интеграция системы автоматизации и управления производством с системой ТАИР или системой технического обслуживания и ремонта. Четвертая стадия цифровизации – это стадия оптимизации, когда уже создается целевой ландшафт цифровой, обеспечивается взаимодействие между всеми системами по единой шине предприятия, осуществляется как обмен данными, так и управление осуществляется через одну единую шину. Здесь начинаются процессы по оптимизации технологических параметров по значениям KPI. Здесь оптимизируется время простоя, оборудования и персонала. Также создаются карты бизнес-процессов предприятия и создаются тепловые карты. Какой из процессов занимает больше времени, почему, и начинается аналитика и оптимизация этих самых бизнес-процессов. Здесь же уже в стадии четвертой идет оптимизация технологического обслуживания и ремонтов. Это переход к ремонту по состоянию от регламентного ремонта по каждое какое-то время. Здесь же очень важно создать общую платформу для ведения проекта, которая бы охватила все 4 стадии. От проектирования, разработки, обслуживания, ну и дальше модернизации и изменения этой самой системы. Также важной частью этого уровня будет переход на модели-ориентированный обмен между системами и между заказчиками. Давайте посмотрим на типовой цикл разработки проекта. Допустим, у нас есть некая система, которую нужно создать. У нас есть некий производитель, который производит некие устройства, например, насос. С этим насосом у нас идут какие-то схемы подключения, есть документация конструкторская, как этот насос выглядит, как его можно разместить в поле на предприятии. Есть какое-то краткое описание, как этот насос работает. Дальше эта документация поступает в проектный институт. Проектный институт начинает разрабатывать схемы привязки этого самого оборудования к технологии, начинает формировать схемы электроснабжения этого оборудования и начинает рисовать какие-то общие алгоритмические схемы взаимодействия. В результате появляется еще проектная документация, который поступает системному интегратору или разработчику. Разработчик, получив эти документы, начинает моделировать. Он создает конкретную модель этого самого насоса, создает модель управления этого самого насоса в системе управления. Дальше он создает модель этого насоса, которая будет представлена на армии оператора. Он разрабатывает модель управления этим устройством с помощью армы оператора. Дальше создаются системы отчетности на основе этого же самого устройства. И после этого уже система тоже с документацией передается заказчику. Заказчик на основе этого же всего создает свои регламенты по обслуживанию, по изменению, ну и так далее, и так далее, и так далее. Здесь важно отметить вот что. Все документы разрабатываются в соответствии с ГОСТами, все здесь достаточно честно и чисто. Однако, если мы вдумаемся, то на каждом из этапов происходит следующее. Мы от реального оборудования переходим к документации. От документации уже следующая компания, пусть будет, да, она переходит к тоже аналитике, тоже создает свою собственную документацию. Эта документация поступает еще дальше, на основе этой документации создаются модели, эти модели снова описываются документацией, и в случае, если у нас вдруг в какой-то момент происходит замена основного оборудования, что нужно сделать? Все правильно, все переделать. Потому что документация не та, не по тому устройству, нарушены там другие модели, нарушено много чего, поэтому нужно все актуализировать. И здесь происходит достаточно нелогичное расходование средств. Это увеличивает трудоемкость. При этом на самом деле все эти, скажем так, контрагенты, они говорят об одном и том же, да, должен быть некий насос, вот он должен работать так-то и так-то. Все говорят об одном и том же, но в силу различного представления на бумаге получается нет ни версионирования, нет преемственности, ну вообще ничего нет. Они на самом деле никак не связаны. И важно еще то, что невозможно приступить к разработке модели более высокого уровня, не закончив документацию предыдущего уровня. То есть все эти стадии, они должны быть выполнены последовательно, а не параллельно. При сложившемся подходе, если мы попытаемся реализовать любую из задач развитой автоматизации, ну, например, создание системы виртуальной пусконаладки для испытания алгоритмов или разработка тренажеров, это потребует, опять же, полного цикла работ от самых основ до окончания. И при изменении основного, опять же, оборудования, все, опять же, участники должны обновить свои результаты работы. Если попытаться представить организационную схему взаимодействия моделей, то она выглядит упрощенно на экране. Опять же, если что-то где-то нужно изменить, ну, например, да, изменить модель представления устройства, то нужно будет изменить все производные модели. Помимо организационной структуры, важно помнить еще и о системной архитектуре. В настоящее время одна из архитектур, отвечающая большинству вызовов современности, является та схема, которая представлено на экране. Внизу расположены системы управления на основе программируемых логических контроллеров с локальной системой визуализации. Чуть выше расположены сервера диспетчеризации и технологические базы данных со своими местами управления оперативного персонала. Они объединены через сеть диспетчеризации. А дальше идет либо сервер взаимодействия с другими смежными системами и смежными организациями через демилитаризованную зону, либо через часть инфодиодов идет передача в корпоративную сеть к предприятию, где также размещаются корпоративные сервера, еще одна база данных и еще одни армы. Исходя из этой схемы, становится понятно, что каждый из узлов имеет свою собственную функцию и свои особенности. А также становится очевидно, что одну и ту же задачу, которую мы делаем, одну и ту же задачу, которую мы решаем, мы должны решить на самом деле несколько раз. Ну, приведу пример. Если мы разрабатываем мнемосхемы управления некой установкой, то мы должны сделать проект и для HMI на самом нижнем уровне, и мы должны сделать проект управления на диспетчерском центре. Мы должны сделать также проект передачи этого самого объекта и этой информации в смежные системы, а также мы должны тот же самый объект разместить в корпоративных серверах. Получается достаточно серьезное усложнение работы. И на каждом из узлов должна быть решена своя собственная задача, своя специфика. Есть. Здесь я хотел бы показать процесс разработки обычной диспетчерской системы. Каждый проект можно представить из нескольких этапов. Да? Мы сначала разрабатываем архитектуру, затем проектируем, затем разрабатываем, затем пускаем в наладку, стартуем этот самый проект или эту самую систему и дальше переходим к обслуживанию. С ходом времени количество неопределенностей или тех возможных изменений, которые будут в ходе проекта, оно непрерывно изменяется, уменьшается, а при этом ответственность за каждое внесенное изменение, чем дальше, тем больше увеличивается. Как правило, системы пускаются к какому-то конкретному времени. Все знают, что, например, пуск такого-то агрегата или такой-то гидроэлектростанции должна состояться, пусть будет в День энергетика, 22 декабря такого-то года, и все работы нацелены на то, чтобы это реально сделать. При этом, при приближении к этой самой дате, количество работы, оно будет непрерывно увеличиваться, и каждое изменение, оно будет затрагивать все другие сделанные изменения. Например, также нужно будет добавлять параметры, настраивать устройство, добавлять уставки, добавлять архивы, обработку сообщений, и так далее, и так далее, и так далее. Много чего. При этом каждое добавление параметра, например, оно занимает некое время. Для простой иллюстрации, для того, чтобы ввести один параметр в систему, необходимо порядка 50 связанных, осознанных операций в системе. И это занимает порядка 11 минут. Поэтому чем ближе мы к дедлайну, тем ценность времени, она возрастает. Как вывод, здесь можно сказать следующее, что оптимизировав инженерный инструментарий, так чтобы простые операции отнимали меньше времени, мы можем сконцентрироваться на действительно важных задачах и можно приблизиться к построению умной цифровизации. Одним из выходов или решением из обозначенных проблем и средством к существенному снижению трудозатрат могло бы стать применение модели ориентированного подхода к взаимодействию между всеми участниками ведения проекта, при котором утверждаются, являются основным предметом обмена именно модели, а не документация, как это принято сейчас в силу традиций. Пример такого подхода описывался много где, и это не вот прям очень свежая мысль. Есть и описания, похожие в шинах предприятия, есть стандарты, например, MAC 61970 или Common Information Model, или это описание стандарта 61850, или здесь можно описать стандарт ICCP TASE.2, но они не вполне отвечают современности. Дело в том, что они ориентированы на межкорпоративный обмен и, как правило, направлены на передачу в основном текущей информации. При этом алгоритмы и модели, они остаются за кадрами и не освещены в этих стандартах. И здесь было бы здорово, на самом деле, если бы со стороны государства появилось бы какое-то финансирование или какой-то грант на создание готового инструментария для сквозного проектирования систем и сопровождения моделей на протяжении всего жизненного цикла, от основного оборудования до создания конечных систем. На следующем слайде я хотел бы показать пример, как мы сделали примерно такое же решение, но в рамках одной нашей компании. Здесь представлено видео. Все модели, они описаны в виде таблицы Excel. У каждого параметра есть, или сигнала, который есть в системе, есть, например, тип этого параметра, наименование, есть наименование, с которым он должен отображаться на мнемосхемах, есть единицы измерения, есть шкалы, есть множество параметров, которые вводятся для обработки в логическом контроллере, есть, ну и другие параметры. С этой таблицей работают одновременно разные отделы нашей фирмы. И проектировщики, и программисты нижнего уровня, то есть программисты контроллеров, программисты верхнего уровня. Все работают с одной единой базой данных, которая описывает, база данных в данном случае вот эта таблица Excel, которая описывает модели поведения параметров в каждой из систем. После того, как мы их описали, с помощью определенных скриптов формируются, как показывается, формируются файлы импорта-экспорта, которые простым способом добавляются в систему. То есть сейчас, например, создается описание информационного обеспечения серверов на уровне системы диспетчеризации. Аналогичным образом создаются проекты для обработки сигналов на уровне контроллера. Вот сейчас происходит прогрузка серверов готового проекта. Дальше автоматически генерируются мнемосхемы для системы диспетчеризации. Они уже расключены, они уже привязаны к конкретным элементам проекта, они уже имеют определенные правила обработки на уровне серверов. И с помощью вот такого подхода можно одновременно легко генерировать мнемосхемы для всех 4 уровней, о которых я говорил чуть ранее. И не только мнемосхемы, да, но и программное обеспечение для контроллеров. И в данном случае вот видно, что что-то меняются уставки, проект, в общем-то, работает. Но одновременно тут можно посмотреть, что строятся и графики, и сообщения, все уже похоже на реальный прототип систем. Для того, чтобы из этой табличной формы сделать мнемосхему, нужно отрисовать статическую графику и разместить параметры рядом с теми узлами, где они реально, измеряются. На основе такого подхода с использованием средств массового инжиниринга автоматически формируются согласованные модели представления данных на различных уровнях системы, как я уже говорил. Автоматически формируется и документация проекта. Мы можем отслеживать версии этих различных изменений. Можем контролировать изменения, вернуться к каким-то изменениям в прошлом, чего нельзя сделать, если у нас проект ведется там стихийно. Также, получается, если необходимо расширить спектр решаемых задач, ну, например, для того, чтобы добавить систему моделирования или еще что-то, то появляется просто еще одна прослойка скриптов для связи с этими моделями. Получается общий доступ для всех участников проекта, и для дизайнеров, и для технологов, и для диспетчеров, и для разработчиков, тестировщиков, аналитиков и инженеров, которые выполняют пусконаладку. Скорость. Да, это немаловажный фактор, о котором я тоже говорил. Вот создание такой системы, примерно которую я продемонстрировал, это порядка 3000 сигналов на один контроллер. Это система управления гидроагрегатом из Минской ГЭС. Мы создали сейчас проект буквально за 5 минут. Причем проект и для контроллера, и для сервера диспетчеризации, и для локальной системы автоматики. И следуя такой логике, у нас не будет ошибок на стыках. Если мы вдруг где-то что-то добавим, мы перегенерируем просто эти модели, и у нас получатся полностью связанные модели как на уровне контроллеров, так и до уровня представления на самом верхнем уровне. И отсюда самое главное, это экономит время, что означает деньги, ну и также повышает качество. Использование таких средств массового инжиниринга в наших проектах позволило существенно сократить разработку за время и внедрение таких больших проектов, как, например, система диспетчеризации на Изминской ГЭС, системы диспетчеризации на Майнской ГЭС, система диспетчеризации и телемеханики на Саратовской ГЭС, на системах диспетчерского управления трубопроводного нефтетранспорта, например, это Транснефть Прикамье, Транснефть Восток и многие другие. Необдуманная погоня за кажущимися выгодами цифровых производств может кратно в десятки раз увеличить трудоемкость создания, поддержания и владения этих систем. Однако за счет использования модели ориентированного подхода, пример которого я описал сейчас, можно на начальном этапе слегка увеличить трудоемкость, например, на 10-15%. Затем существенно сократить трудзатраты при внесении изменений, масштабировании, что особенно важно на долгосрочной перспективе. У меня все. Спасибо. Вопрос, пожалуйста.
Спасибо большое. Очень прикладной доклад, крайне актуальный. Спасибо. Коллеги, вопросы?
Спасибо, Виктор Евгеньевич. Очень интересный доклад. Но вы рассказали, вот как эти проекты реализуются с нуля. А вот там, где надо сейчас в этих условиях заместить уже оборудование, используемое для ШТП. Я поясню, вот в Арктике, например, нефтегазодобывающих платформах, у них стоит оборудование фирмы Siemens. Мы пытались интеграцию с системой безопасный город и так далее, но вся документация закрыта, все вот эти технологические решения тоже не подлежат. Есть ли подходы вот к этому делу? перейти на отечественные решения, не шикарные. Наша Маинская ГЭС, Красноярска, работать знаю. Вот. То есть там какой должен быть системный подход. Трансформировать то, что вы сказали, или с нуля что-то прорабатывать на вот этом научном теоретическом уровне. Спасибо.
Спасибо за вопрос. Ну, на самом деле, ответ на него должен был прозвучать в презентации. Возможно, я не сильно акцентировал на этом внимание. Первый этап – это все-таки зафиксировать существующее положение дел. Если есть система, работающая система на Siemens, на неважно на чем, на любом западном оборудовании, нужно в первую очередь разобраться, как она работает. Она уже работает. Да? Нужно построить некую модель, нужно реконструировать алгоритмы, которые заложены в эту систему. Если это частный какой-то случай, да, например, это предыдущие линейки контроллеров Siemens, то там можно полностью восстановить код. То есть можно совершить процесс реверс-инжиниринга с помощью этих алгоритмов, создать модели управления и дальше уже понимать, каким образом эти алгоритмы могут быть перенесены в новую систему, на тот же самый регул или на другой производитель контроллеров. В общем-то, нормальная система и нормальный подход, который ему сейчас следуют практически все современные производители.
Спасибо, спасибо. Тогда, если можно, краткий еще один вопрос. Большие языковые модели или там, в принципе, вот генеративные модели как-то используете в своих подходах?
Нет, не используем, пока нет.
Понятно, понятно. Ну, потому что, в принципе, это хорошо матчится с там, большими отраслевыми моделями, как раз там для построения конструкторской документации и так далее. Спасибо. Спасибо большое за прикладной доклад. Спасибо. So, we will switch to our next presenter. Dr. Maria Antoinetta Pascali, researcher of Institute of Information and Science and Technologies of Pisa, Italy. So, Dr. Maria Antoinetta, hello, and please.
Good morning.
So, yes, we hear you well. So, please, you can start.
Thank you very much. I'm Maria Antoinetta Pascali, a researcher from the National Research Council of Italy. I would like first to sincerely thank the organizers for the invitation and you all for being here. In this talk, I will report about topological machine learning and its application in the biomedical domain for the analysis of data from Raman spectroscopy. Okay. This talk is divided into two main sections. The first one will provide the audience with the base concept of computational topology, from persistent homology to its combination with machine learning for classification. While in the second part, I report about the promising results obtained in two challenging case studies: bone cancer detection and grading from Raman spectroscopy of bone tissue, and the detection of the Alzheimer's disease from Raman spectroscopy of the cerebrospinal fluid. Okay, let's start with the basics. Topology is a branch of mathematics able to inform us about global properties of data, even in presence of noise. Topology is the correct framework for the mathematical formalization of very important concepts related to our experience of the real world we are familiar to, such as neighborhood, continuity, and connectedness. More important, topology provides invariants which pick up the shape of an object despite countless variations or deformations and noise. With algebraic topology, we are able to look for intrinsic qualitative aspects of spatial objects that remain invariant under homomorphism, which are both directions continuous one-to-one transformations. The most famous and studied topological invariants are the Euler characteristics and the Betti numbers, which are strictly related to a very important class of invariants, the homology groups, which encode a great deal of information while still being efficiently computable in many cases. To exploit computational topology for studying real-world data and shapes, we need to represent our considered data as a simplicial complex. A simplicial complex is built from points, edges, triangular faces, and so on. Abstract simplicial complex could be seen as a very useful representation of several kinds of data, from images and shapes to high-dimensional data sets. In computer graphics, the simplicial complexes are very commonly used as they are meshes. Intuitively, the homology group in dimension 0 counts connected components, while in dimension 1 it counts loops, and in dimension 2 it counts two-dimensional voids, and so on. Okay, I see that. Okay, the slides are not respecting the poinsettias of the character. Okay, are you able to read anyway? Even, or may I share my presentation from my PC? I don't know. Maybe if for you it's fine like this, I will continue. Okay. A few decades ago, algebraic topology was enriched with the core idea of persistent homology, using homology groups to explore and track topological attributes of an object across scales. In general, the success of persistent homology is due mainly to a few reasons. The persistent homology is found to provide powerful topological invariance successfully applied to data analysis. There exist good algorithms, just linear algebra, for computing persistent homology, increasing scope and speed. Most of these algorithms are well implemented. Now I would like to show an animation, but I see that this is the PDF file. May I upload the PPT files in order to have this animation correctly shown? Okay, so the idea of persistent homology is simple. With the simplicial complex associated to our algebraic representation of the investigated object, and join nearby points. Okay, we have to choose a distance and build balls in order to connect correctly the pairs of points that are no farther apart than D, and fill in complete simplices. Okay, after that we can compute homology, which enables us to detect the hole, the big hole in the middle, because the points in the plane were just a sampling of the circumference in the Euclidean plane. Okay, but now we have a problem. Yeah. How do we choose the right distance? D? Yeah. If D is too small, then we detect noise. Yes, we have many connected components, one hole, but the hole on the left upper corner is not the right one we want to detect. And if D is too large, then we get a giant simplex complex, which has a trivial homology. Hence, okay, there is quite a good distance that we may choose. But how do we know this all is significant and not noise? We a priori do not know. The idea of persistent homology is to consider all distances D to track shape across the scale. Okay. Now we want to understand how it is possible to read this persistence. The visual representation of this persistence is easily visualized with barcodes. Each O appears at a particular value of D, and this appears at another value of D. D1, we see that a hole appears in the middle, and D2, okay, simply is complete, and there are the hole disappears. We can represent the persistence of this hole as a pair D1, D2. We visualize this pair as a bar from D1 to D2. Okay. A collection of such bars is a barcode. Okay. Try to record such a barcode for the previous example. Okay, you see there are short bars which represent noise. And after that, we see the long bars starting representing the main feature, the loop. We are looking at homology groups in dimension 1. Okay. And in the end, we'll get the trivial homology. Okay, an alternate representation of such barcodes is the persistent diagram. Instead of drawing AB as a bar from A to B, we simply draw a dot at coordinates A and B. Okay, the previous barcode now is represented as a set of 3 points in the Euclidean plane. Okay. Now, persistent homology has many nice properties. It can be visualized as barcodes or diagrams, which can be compared efficiently using proper distances, such as the bottleneck or matching function or the Wasserstein distance. And also, more important, persistent homology is stable with respect to small variations, and it is computable with linear algebra. And algorithms are currently implemented in several open and free software. Okay, here you find the first statement of the stability theorem in the very specific setting of Morse theory, which has been further generalized a few 10 years ago in the persistent theory in the more general version. Okay, here you may appreciate in this simulation the direct consequence of stability. Persistent diagrams are robust against the sampling randomness of a circumference in the plane. You see that the first dimension homology groups, the red dots on the right, move a little bit, but the very important feature that is the farthest from the diagonal is still there, very detached from the other points. Okay, in what I said previously, I intentionally avoided saying that persistent homology may be computed, make different choices about complexes, and how to build them from points sampling our data. I won't go into such technical details, but I want to let you know that depending on the type of data you are considering, one choice may be better than another, for example, regarding the computational effort. For example, from a computational viewpoint, the RIPS complex, which is a flap complex, is less expensive than the corresponding check complex, even though the RIPS complex has more simplices in general. Okay, the first algorithm to compute such groups has been proposed by Zomorodian and Karsh in 2005, and the diagram, we already said that is computable via linear algebra, and the runtime of the algorithm is O(n) to the power of 3. Okay. Just to recall the bottleneck distance. A a persistent diagram actually is a set points in the plane, a multi-set of points, because we have to also count them with multiplicity. Bottleneck distance measures the similarity between two persistent diagrams. And it's here you see the correct definition. But in a few words, it's the shortest distance for which there exists a perfect matching between the points of the two diagrams plus all the diagonal points, such that any couple of matched points are at a distance at most d, where the distance between points is the superior norm in R2. And this is not the Euclidean distance. Okay, one basic goal is to take advantage of such representation capabilities of persistent homology to use the features it provides for solving classification problems. The space of persistent diagrams can be endowed with metrics. We saw we can use the bottleneck of the p-Wasserstein distance. However, there is no natural Hilbert or Banach space structure on it. And such metrics tend to be computationally prohibitive or require the use of complex approximation of algorithms. Then we can't perform estimators for understanding statistics, and we can't directly use persistent diagrams into classification problems. As we know, that machine learning classifiers expects input data to be vectors of common dimension across the classification problems. A natural way is to use representation methods to convert PHT diagrams into vectors. And this is the appearance of the persistent homology pipeline combined with machine learning. Okay. Hence, recently, a lot of attention has been devoted to vectorization of persistent diagrams through the construction of either finite dimensional embeddings, namely embeddings turning persistent diagrams into vectors in the Euclidean space RD, or kernels, namely generalized scalar products that implicitly turn persistent diagrams into elements of infinite dimensional Hilbert spaces. Here I listed the most known and used in literature with reference to the paper in which they were introduced. Okay, I will skip this slide about vectorizations because they're maybe too technical. Okay, they have different properties. Some of them have nice statistical properties. Some others are easier to compute. Okay, the problem is that when we have many ways to turn persistent diagrams in vectors, but we don't know a priori when we have a specific classification task to perform with a specific data set. We do not know which is the best way to represent the data set in a data set of vectors in order to optimize our classification performances. Okay, we have introduced a theory, persistent homology, to study and analyze data. We have defined robust invariants, visually represented by barcodes and diagrams, and we have tools for their practical computation and methods for turning invariants into vectors. Everything is ready to apply them to data for pattern recognition and analysis purposes through machine learning, as sketched in this slide. The user may select the appropriate filtration for computing the persistent diagram based on the type of data. After that, many vectorization, all the possible vectorization are computed, and we should keep in mind that we have to consider all non-trivial homological dimensions. Such vectors are fed to machine learning classifier, and after that, the optimal couple vectorization classifier is selected via a grid search approach. Okay. Here, I just want to mention the supervised machine learning classifiers that we use to build the topological machine learning pipeline, which are the lasso, random forest, and support vector machines. Okay. The paper cited below includes not only a detailed description of what I said of the topological machine learning pipeline, but also a thorough experimentation with benchmark datasets. The first dataset we tested in our study comes from data arising from a discrete dynamical system modeling fluid flow. The dynamical system here represented is a linked twisted map, which is a Poincare section of a negameter type flow. A Poincare section is the discretization of a continuous dynamical system obtained by following the path of a particle's location at discrete time intervals. The equations for the linked twisted map are those you see in the slide here. Okay. Depending on how different orbits are created. And these orbits might be dense in the two-dimensional square, or voids might occur. Here, the task is to classify the value of the parameter R based on the orbit. Okay, now you see the dataset used is composed of 5 different values of the parameter R: 2, 3.5, 4, 4.1, and 4.3. Each with 50 orbits generated from different random starting points, the seeds. Each orbit consists of 1,000 points generated from 1,000 iterations of the linked twisted map. Here we see 5 orbits generated using the same R, but with different seeds. Okay, for the dynamic dataset, the TML pipeline appears as in the picture. We use the alpha complex, which is a simplicial complex constructed from the finite cell of a Delaunay triangulation. Also, we use 4 types of vectorization in dimension 0, 1, and also we leverage both dimensions using 2 techniques, namely the fusion and the concatenation. And finally, the classification step is performed with the lasso, support vector classifier, and random forest with varying parameters. Okay. Via a grid search approach, the optimal parameters of vectorization classifier are selected and the performance accuracy has been assessed using a 10-fold cross-validation scheme. You see here in this table the results. And in the end, the best performing combination of vectorization method and classifier is found and tested with accuracy results reported in the table. 0.92 is the best result. And the dimension used is the first dimension, of course. In conclusion, such results obtained by the pipeline in the dynamic dataset are very satisfactory regarding both classification accuracy, and if you come back to the previous table, and also regarding consistency of the best performing representations. Okay, let's move now to the second part of the talk and to more interesting data, Raman spectroscopy in medical applications. Raman spectroscopy provides information on molecular vibrations, fingerprint of molecules, exploiting the inelastic scattered light by the sample Stokes and anti-Stokes Raman scattering under a visible or near-infrared laser irradiation. Then Raman spectroscopy is used for molecular identification, structural changes, folding states, and so on. Strengths of Raman spectroscopy are that Raman spectroscopy provides an ultra-sensitive molecular characterization. It is a label-free method and non-destructive. Of course, there are some limitations when applying Raman spectroscopy to a biological sample. Biochemical information may be too rich, there may be subtle differences between Raman spectra of different samples, and on the other hand, there may be a high variability between Raman spectra within the same sample. Hence, data interpretation is a challenging task. We tested the topological machine learning pipeline in the following use cases. These, of course, are joint works with other research groups in Pisa and Florence. Okay. These medical applications are the detection and grading of bone cancer and the detection of Alzheimer's disease from cerebrospinal fluid. Okay. But can topological machine learning exploit Raman spectroscopy information? Okay, let's try to apply our method. Raman spectroscopy data have been associated to a simplicial complex using the two filtrations, the lower star filtration and the one-dimensional version of the dilation filtration. Persistent diagrams have been computed, and the optimal vectorization parameters and machine learning classifier are selected via a grid search approach. Accuracy results are computed as the average over a Lee-1 patient-out cross-validation scheme. Okay. The first case study is the chondrogenic cancer. Chondrogenic cancer is the second largest group of bone cancer. They differ in malignancy grade and the correct classification between non-cancerous version and chondroma and primary chondrosarcomas, chondrosarcoma group 1, as a critical issue for pathologists. Raman spectroscopy represents a fast, efficient, and non-invasive diagnostic tool. Chondrogenic tumors produce a cartilaginous matrix in the bone that is detectable by Raman spectroscopy. Hence, we may have chance to correctly perform our task. And the task is to grade chondrosarcoma and to distinguish chondrosarcoma from enchondroma. Here you see sample tissues of each grade groups and of enchondroma. Okay. The study population in this case is made of 20 patients equally split in the 4 classes. 10 of these patients constitute a total of 400 spectra that have been used as training. The remaining 10 patients, each one with only one spectrum, are used as test in order to simulate the clinical the application in the clinical scenario in the real world. No preprocessing has been applied to such spectra, and different acquisition machinery has been used to collect the training and test dataset. And a priori, we may have a mess in these results. Here we show the classification accuracy results assessed using Lee-1 patient-out cross-validation scheme and assessed using a trained model to classify never seen data from 10 new patients enrolled in the study. You see that our results, the best results with 2 labels, are confirmed in the test set, and 80% is quite a good result. The results strongly support that Raman spectroscopy and topological machine learning may provide an effective combination for the chondrogenic cancer grading. The results are better than we can read in bibliography, and both for labels classification and 2 labels classification performance were good when trained on a large enough dataset. And the next step, of course, should be to enlarge the dataset to provide more robust and conclusive results. Okay, the second case study is the Alzheimer's disease, which is the most common neurodegenerative disease, and its diagnosis currently requires a series of neurological examinations, while the definitive diagnosis is possible only post-mortem. Raman spectroscopy represents a fast, efficient, and non-invasive diagnostic tool from cerebrospinal fluid, CSF. And, of course, this study is being carried out in the framework of a regional project, which is PRAMA, Proteomics, Radiomics, and Machine Learning Integrated Strategy for Precision Medicine for Alzheimer's, funded by the Tuscany region. Okay, in a previous study published in 2023, our study population was made of 24 patients, of which 19 have been diagnosed with Alzheimer's disease, and the remaining only five cases are considered as controls. Even with such a small and unbalanced data sets, we achieved with topological machine learning an accuracy of 87% using assessed using Lee1 patient out validation scheme. Further experimentation here reported show that our classification method is stable, and this study confirms the previous results. Here, the study population is made of 43 pathological subjects, 21 with Alzheimer's disease and 22 controls. For each patient, a set of 10 spectra have been collected for each drop-casted sample, and the average of such spectra has been computed. Regions of salt have been removed, you see in the cropped graph. Has been removed from the spectra. After that, a baseline correction and a statistical smoothing filter have been applied. Then standard signal analysis transformations were performed on the spectra, Fourier transform, Welch, and correlation transforms. Okay. Here, the topological machine learning pipeline is more complex. The classification part of the topological machine learning pipeline is made of several machine learning classifiers, which are all trained across all the vectorization computed by the first part of the pipeline. We achieved here an accuracy of 86%. Also, the ablation study here reported shows that a simple machine learning or one-dimensional CNN achieve results largely below our method. The results in this second case study strongly support that RS and TML may be a reliable and effective combination to confirm or disprove a clinical diagnosis of the Alzheimer's disease from CSF. Our methodology may evolve, of course, in automatic support to Alzheimer's disease diagnosis, which could be easily embedded in a commercial platform of Raman spectroscopy. Results as outperform what we found in bibliography, which is reported in a paper by Rizikova and colleagues published in 2021 and achieving 84% of accuracy. And next steps are to enlarge, of course, the dataset of CSF samples to validate the proposed method better, and eventually to understand if TML could characterize AD subtypes. Okay, in conclusion, we introduced topological machine learning for the analysis of Raman spectroscopy data. We demonstrate the efficacy of TML both in Alzheimer's disease detection via CSF analysis and in bone cancer detection and grading. The robustness of TML inherited by the stability of topological feature extracted from input data has been showed not only against signal noise of the Raman spectrum, but also against dataset small size and data imbalance. And TML pipeline in these two case studies achieved superior performance than state-of-the-art literature. Sorry for taking too much time. Thank you for your attention, and these here you find if you're interested.
Thank you, dear Dr. Pascalia. So very interesting presentation and very rapidly development sphere of computational topology in machine learning. Yes. So do we have any questions in the room? Okay, so I have a question, at least one. When you told about machine learning pipelines combined with computational topology, you tell us about SVM, lasso, and random forest. And is it possible to integrate some computational topology algorithms inside of stochastic gradient descent or backpropagation?
Yes, actually, the current direction of research in this topic is to build not topological machine learning, but topological deep learning. In fact, there are many results of topological layers which are embedded in deep learning architectures. So in our lab also we performed a few studies in this direction, but it's quite messy. Too early to understand its potential. We are studying it. Very interesting.
Okay.
Yes,
maybe you have some experiments in PyTorch, for example.
Yes. Okay. Also, these methods could be also used in order to look for topological uncertainty, because such kind of methods are quite efficient for studying graphs. And if you look at, for example, activation graphs in deep learning architecture, you may study the data set and find outliers or understand if there is some anomaly in the topological structure of activation graphs. So it's la research quite new, and I think that the main strength is that the basics are intrinsically complementary to many to the methods we generally use in learning and machine learning. So we may expect to have complementary information and hence to get very important results. Thank you.
Okay. Thank you for discussion. Do you have any questions more? So, okay, dear Dr. Pascali, thank you for your brilliant presentation, and so we will continue. So our final presentation in this section is also from Italy, Professor Simone Bianca, professor of University of Milano Bicocca, Italy. So he will discuss some machine learning approaches in digital camera pipeline optimization. I think it's very interesting presentation. So Professor Bianca, do you hear us?
Yes, can you hear me?
Yes, fine. And good morning. Oh, hello.
Good morning.
So you can start, so please.
Okay. So thank you very much for your invitation and for this introduction.
Thank you.
The work I'm presenting today is expert-driven versus machine learning approaches in camera pipeline optimization. The main question that we try to answer is that we know that nowadays machine learning and deep learning are used for almost any task in any different research field. The question is if there is still room for some knowledge come from experts in the field that could add something that is beyond what deep learning can do, or can do it in a more way, since we are adding domain knowledge. Okay, so first of all, we are all used to acquire images, digital cameras and digital phones, but we are used to see the final results, the final rendered image. That is what we actually see on. But actually, the image that the sensor acquires is completely different from that one. And we need to process this image in order to actually give as a result a good image to the final user. What you see here, the sensor image, the picture labeled number 1, is actually what is coming from your sensor. So it's a very dark information, and it contains a lot of art. And we call all this pipeline a rendering process, since the final goal is to actually render a digital image that is suitable for viewing and for sharing. So a digital camera processing pipeline consists of a series of steps that the digital camera has to perform to process the raw data that is captured by the image sensor into the final image. And this pipeline is responsible for applying various adjustments to the image, such as, for example, correction for imperfection in the lens. So they could be geometric distortion correction, or also not uniformity correction. Because remember that actually, compared to that of reflex lens reflex cameras, the lenses are very, very tiny, so they contain imperfection, or some white balancing, or some reduction of noise, sharpening, and so on. Mm-hmm. So although we have that manufacturers may use varying algorithms and strategies in their pipelines, more or less, we have a sequence of basic steps commonly involved in all the digital camera processing pipelines. So as the light enters the lens of our camera, this lens is projected on the sensor, which actually, for a given pixel location, just acquires one color information. For example, red information, green information. But actually, in order to display an image, we need that at every spatial location, we have all the 3 information simultaneously. So from this filter array, we need to recover a full red, green, and blue image. And this is what is called RGB demosaicing. We have to perform some operations about noise reduction and to conversion of this image into a standard color space. Because the particular manufacturer, we have that each camera sees colors in its own way. So a given green actually results in a digital count from sensor to sensor. And we need to actually translate this color into a standard color space. Otherwise, when we are going to our images, for example, of a red rose, we are going to see the rose with a given red, and our friends are going to see a different shades of red. After this, we have all the operations that say are preference-based. So we could have some photo finishing, because maybe we want to enhance colors, or we want to desaturate them to look more neutral. So all the, let's say, filtering operations to change the real use of the color. Then we have a final compression into a compressed format that could be JPEG, and then we have the saving operation. So Actors actually uses proprietary algorithms in all these steps in the pipeline, but more or less the sequence of operations is the one depicted in the image. And each one of the algorithms that composes this pipeline, so here we have demosaicing, noise reduction, and so on, contains some parameters that have to be tuned for the particular sensor. And what happens is that usually these parameters are optimized by the manufacturer for daylight scenes, so or for other very specific use cases. So in general, when they design a new, they tend to acquire some images under daylight conditions and to tune their algorithms for this new sensor. So what happens is that even if we give the same sensor to different manufacturers with the same pipeline, it means that manufacturer one will tune the different parameters in such a way to obtain a given look of the final image. And if we give the same to another manufacturer, this will obtain a completely different results, okay? This is just based on the preference of the manufacturers and the engineers to tune or optimize this processing pipeline. As you can expect, many modules that this pipeline are very challenging since they try to solve some very under-constrained and ill-posed problems. For example, if you take an estimation, if you do not have enough context, you cannot understand if you are photographing a white wall with a yellow light, actually a yellow wall with a white light. Okay, so they try to solve some problems that are inherently ill-posed. And this is why traditional approaches for these modules across the years have been substituted with deep learning-based approaches. What happens is that these deep learning-based approaches actually are able to improve module by module the results with respect to traditional methods, but have drawbacks. First of all, they lose interpretability because they are introducing very complex models based on a very large number of parameters. So understanding how to tune them for a particular sensor could be very challenging. And on the other side, since each one of these models is the isolation, there is no way to exploit existing crosstalks between modules. For example, we know that if we apply a noise removal filter that is too strong, we are going to also reduce the spatial detail. So we will need to actually implement a sharpening algorithm that brings back the details in the image. And so noise reduction is not a problem that is completely isolated from image sharpening. So this type of crosstalk is something that if you develop one algorithm for one processing module in isolation, you are going to do. So let's see what is the problem on which we are focusing today. Our problem is that of enhancing night scenes. So you remember that we have said that usually manufacturers tend to tune their pipelines for daylight images, but actually many of the images are taken during nights. In particular, our task is that starting from the input image that you see on the left, to obtain an image that, let's say, has to meet some aesthetics requirements. So we want to keep the naturalness of the scene, and also we would like to improve the aesthetic of the photos. So we are not interested into generating a new type of image in which, for example, some parts are more readable. So we are not using a license plate reader for a given parking, where actually our focus is to being able to read our license plate. What we want is obtaining a version of the image which respects its mood. So we still need to understand that this image has been taken. We do not want to process it as it was taken under daylight, and we want to preserve this mood. Okay, so we want to keep some aesthetic this type of images. From the pure technical point of view, when we analyze nighttime images, we have challenges that actually we have to face in comparison with other approaches at scenes. For example, night images tends to be much darker, and this can be results in images having a low signal to noise ratio, so more noise. And so it would make extract useful information from the image more challenging. And we have that color casts are generally present. The fact that we have many different sources of lights in the scene, while in daylight images, we just have one main source of light, which is the sun. Here we have many different lights with different colors. And also, due to the fact that at night, the amount of light that reaches our sensor is very, we need a very long exposure. And this may cause some shaking of our hands, of our device, resulting in blurry images. So let's see what are the main approaches that have been proposed recently in the state of the art. So we have said that recently, all the different steps have been replaced by methods based on deep learning. In particular, we have all the different shades of deep learning methods. We have, for example, methods based on convolutional neural networks trained with paired images. So we have an input image and we have a design output with which we want to compare. Then we have, in the case where we do not have paired data, some approaches based on generative adversarial networks. So in this case, there is no need of having the actual ground truth, but actually we have some samples of the same scene, but other scenes taken and processed as we would like. There are also methods that try to combine the so a sort of semi-supervised model which integrates both convolutional neural networks and generative adversarial networks. And also we have recently the proposal of some zero-shot learning methods which actually try to eliminate completely the requirement of paired and unpaired data. All these methods suffer from several problems. For example, over-enhancement, some color distortion, loss of details in the final image. But the most important part is that they are very heavy from the computational point of view. This would reflect into a very high memory consumption, which will into a very high energy consumption on your device, which will make this type of methods actually not suitable in digital cameras and smartphones, where your energy comes from the battery. So it's not possible that you just to take a few images are completely drain your battery. So you need to design something different from this. So we go to what is the solution. Our solution is that of using a pipeline for rendering of visual pleasing photographs in low light conditions, which contains several algorithms that try to address the challenges that are presented here in low light images. In particular, we proposed a so-called traditional processing pipeline, so where the algorithms are designed by experts. And in particular, these main modules are designed on one side on the basis of the knowledge of the mechanism of human vision. So it tries to, let's say, imitate what happens in the visual system, and also on the basis of our knowledge of the million of the imaging devices itself. And what's more important is that this pipeline is characterized by a very shallow structure and by a very low parameter count. So what happens to these very few parameters? As they are very few, these parameters are heuristically set by experts in the field according to their personal preferences, and also with avoiding any reference to existing data sets of low-light images corrected by human experts or some automatic approaches. So it's just set on the basis of our personal preferences. And the fact that we are developing something that contains a very low number of parameters to be tuned makes it very flexible, as this can be potentially tuned to match the individual user preferences and also different sensors. So let's see what is actually our pipeline. The proposed contains some known processing steps, which is against neural networks, where actually the exact operations that are done in modules are not known, since they are black boxes to us. It contains a very shallow structure and a low number of parameters. In particular, it contains two main parts. We have the first part, which is delegated for the raw processing, which actually performs some operation on our images. And then we have the second part, which is very specific for night images rendering. We have the first part, which contains a denoising operation. As you can see, we have denoising, and we know that after some steps, we will sharpening, because denoising is going to reduce the sharpness. So it's going to reduce the amount of details that we have in our image. There is a contrast enhancement operation, which actually tries to increase the visibility of the elements inside the image. Final step, we have an automatic white balance in order to give the final look at the mood in the image. Now, let's review all these more one by one in order to have an idea of how many free parameters they contain. So first step is denoising. Okay. For denoising, we are using a non-local mean, but applied in the same way the human visual system behaves with respect to the luminance channel and to the chromatic channels. So we identify of having a method that behaves with different strengths on the basis of the luminance information and the information. So starting from an input image, we convert it into YCBCR color space, and then we process in the luminance channel and the chromaticity channels. For both of them, we estimate the amount of noise present in the channel, because it may happen that actually we have some gray level noise and also some chroma noise, and they could be of different. On the basis of this, we design two different weights, one to be applied on the luminance channel and one to be applied on the chromatic channels to obtain a denoised version of these channels. When we have performed this operation, we transform the image back to RGB for further processing. Okay, so here substantially we have two free parameters that are the weights to be applied on channels. So the weights which reflects how strong the denoising operation should be. This is an of the application of this type of filters to the final image. So on the left, we have two crops of images where noise is very visible. In the middle, we have an RGB denoising, so without a different operation on the chromatic channels and luminance channel. We can see that the sky is very flat, so we were able to remove the noise, but this comes at the price of losing. You can see here on the balcony and on the steps that many very fine-grained information is missing. On the right, instead, you can see the results or approaches which decompose the image into YCBCR. You can see that the sky is very flat as for the previous image, but we are not losing any spatial details, or we are losing much less with respect to the previous example. Step is about contrast enhancement. In particular, this is not a single step because we know that many algorithms introduce some artifacts that have to be corrected. So this contains different algorithms that have the task to enhance the image by manipulating the corresponding histogram statistics. So starting from a very dark image, we want to end up with a more image. Okay, so first of all, we apply what is called the local contrast correction. Also, this is inspired by how human visual system works. So we are not applying actually a global correction of our visual stimuli, but actually we are performing a local adaptation on the basis of the local contrast. So these algorithms work in the same way. So starting from the input image, this is converted to YCBCR color space. And starting from the luminance channel, we actually apply a Gaussian filter to obtain a low resolution version of how much light in each region of the image. Then this is inverted and used as a local gamma correction in order to obtain a local linear correction. The second step that we apply is that of setting the global mean contrast with an S-curve correction. So we want to perform a contrast gain around the mean. This is the fact that we know that the previous algorithm tends to squeeze the final histogram of the image. So we want to actually expand, and we do not want to change the mean of the algorithm. We just want to increase its visibility without performing global adjustments. So we apply a contrast gain around the mean, and then we apply an S-curve to perform different type of operations on dark colors and on lighter colors. Then perform a subsequent histogram stretching operations. This is an operation, normalization, which is done to the percentiles of our histogram in the image with one extra condition. So depending on what is the percentile of our image, we actually perform this operation by considering a different value for this Vmax that we have in the denominator. So if the percentile 99.99 is between 0.7 and 1, then we use as Vmax our percentile, which is 99.99. Otherwise, we are going to use this previous So this is adaptive with respect to the position of the histogram. Then we apply another contrast correction. So depending on the mean value of the luminance channel that we have at this point, we are to apply this conditional contrast correction. So if the average in the image is lower than the threshold, this means that the image is too dark and we need a second S-curve to brighten the image. Instead, if our mean is higher than a given threshold, this means that the image is too bright and we need a gamma correction to darken the image. You can see here on the left, in this image, we have lost the information that this image was taken during night. So the content is clearly visible, but this is not our task. The user took this image during night, and we still want to preserve that night mood, not want to render it as it was taken during the daylight. So if we check that this image has an average value that is too high, we are going to darken this image in order to bring back the mood of the night scene. As final step, we are going to perform a sharpening operation. This is done in a very simple way using unsharp mask to bring back some of the details that we have. So we apply a Gaussian filter to obtain the low frequencies. We obtain the high frequencies, which are multiplied by a weight and added back to our original image. So a standard unsharp masking algorithm. So let's review also the very final automatic white balance, which has the task of giving the final mood in the image. So we need to actually estimate what is the luminance, since we do not want to give an image as a result that contain a global cast, but we want to preserve the information coming from very chromatic lights, as you can see here in the bottom right of the image. And in particular, the examples here on the are those obtained by our pipeline. So you can see that we have some snow here. The snow appears to be white, is not containing any color cast, but also we are preserving the color of other chromatic lights. And more or less, this is the behavior of the human visual system are in this type of scenes. So more or less, we tend to balance those images with respect to the main light in the scene, but actually we are still able to see very chromatic lights. So let's see how many parameters our pipeline. So in total, we have 14 parameters to be tuned. And just to have an idea, this contrasts with recent deep learning based methods where they have millions of parameters to be tuned. So this is why here, by having this number of parameters, we are able to put our knowledge in the domain and to tune such a pipeline, while those type of actually have to perform a very intensive training phase in order to properly tune their algorithms. So what is the dataset that we have considered for our experiments? We adopted the dataset that has been used in the entire 2022 Night Photography Challenge, which contains 250 raw RGB images of night scenes captured with a Canon single lens camera. And in particular, the results that is given, it's raw images at 16 bits. Due to the natural challenge, the ground truth images are not available. So there is no desired target. And this is the perfect test bed for our type of solution. We just have 14 parameters to be tuned without having any ground truth. In particular, the organization of the challenge divided 150 images into different sets. They could be used for training, for validation, and keep 50 of them for testing, and are respecting the same split in order to be comparable with results from the challenge. Look at the results. So we evaluated our pipeline by comparing it with some state-of-the-art approaches for image enhancement, and also with other solutions that participated in the entire 2022 Net Image Challenge. Since no ground truth are available, the only way in which we could assess the results is that of performing psychovisual comparisons and mean scores or experiments. This is actually the same procedure that has been applied also for evaluating the challenge, because not having ground truth is the only way we can assess the results. In particular, we selected 8 recent state-of-the-art approaches for low-light image enhancement, and we our psychovisual evaluation test using the same 50 images from the validation set, which have been processed by all the different methods. More precisely, here we reported the names of the different methods. So very famous, we have kind and kind plus plus, we have GAN, we have 0DCA and DCE plus plus. So as you can see, they are, as the name suggests, representative for different approaches in the part. Okay, so we have some zero-shot learning approaches, we have some GAN approaches, and we have some CNN-based approaches. So by running our experiments on a pool of 50 different users on Amazon Tark, this is the result of the preference of the users. So in purple, you have the amount of preference of our method with respect to the others. In particular, you can see how our solution recorded a total amount of preference of about 45%, which means that on 45% of the images in the dataset, our method was the one achieving the best results according to the user. So it was the one that for the user was more visually pleasant. Then we have as second the 2 versions of 0DCI++ and 0DCE. Then we go into XCNet, and all the others have just a few images on which they are the best. It's interesting to see that all the methods have been considered to be the best one on some of the images. Okay, so this is something interesting. So even the worst methods actually are the best ones on some type of images. But actually, this is a very difficult task because all the methods results to be the best one on a given pool of images. Here's some results. Okay, on the left, for example, we have the 16-bit raw input of one image. On the right, our final image. As we do not have this greenish cast anymore, and we have preserved the fact that this image has to be taken during night. We see all the different chromaticity of the different lights that we have in the scene. These are also some other results where you can see that actually the image, it's clearly visible, the content, not, for example, in this two, but in our, it's the case. And also in the final one, the image is not too bright because we want to preserve the mood that this image has been taken during night. Also some other examples where you can see that we were able to successfully remove any chromatic cast unwanted because we want the snow to appear as white as it would appear to us if we were in the same scene. So it's unlikely that a human would see some this on the left with this very yellowish cast. It would see something more like this one. So the snow that is almost white and chromatic lights. This was my slide. So I would like to thank you for your attention during this presentation. And I would like also to thank my colleagues because this work has not been done just by me, but also with my Simone Zini, Claudio Rota, Marco Buzzelli, and Raimondo Schettini. So thank you very much.
Thank you very much, Professor Bianca, for your brilliant presentation and very interesting pipeline, very classical pipeline without any neural networks. And you show us that the results of this procedural or classical pipeline is preferable in most of the cases when you check it using human evaluation, yes. And so let we switch to the questions. And my question is, what about the computational cost of your method? Is it possible to use it in real time for video processing?
Okay. At the moment, the pipeline has not been optimized for real-time processing, but actually the methods that are used are not heavy from the computational point of view. So be easy adapted for a real-time processing also on video. Of course, using videos, you will have something more to put into this pipeline. You need to actually implement some sort of temporal coherence in your correction because you do not want to have differences in correction frame and the next ones.
Yep.
So there will be some additional steps to adapt this to a video processing pipeline, but we are confident this could be easily optimized for running in real time.
Okay, thank you. And probably it's maybe it is a good idea to combine it with recently popular learnable lookup table approach. Is it possible?
Yeah, that could be a very likely extension because, let's say, in this pipeline, many operations are just done on in order to estimate the parameters. So that could be a very nice extension to adapt it to recent work that actually employ lookup table and let's say some also neural based lookup table approaches. So yeah, that's probably our next step of enhancement.
Okay. Thank you again. And do we have any other questions, Igor?
Hi, Simone. Thank you very much for your speech. It was a pleasure to see the results of your work. And I have two questions. First one is about this approach. In my feeling, the small amount of parameters, this is a good news for us. Yet we see that almost all modern community trying to do end-to-end neural-based pipeline. But indeed, they do not have good data sets. In your opinion, what the next step will we see in development of this area? Maybe it will be somehow connected with a new perceptual metric, which will allow us to have large data sets, or some unsupervised style. Any forecasts will be interesting.
Yeah. My opinion is that we are going towards the personalization of this type of pipelines. So it's unlikely that sets would work for every one of you there at the conference, for example. Maybe you like reds to be more red. Someone would like neutral tone. And so the same preset of the camera is not working. So it's more likely that you want to, for example, by showing 10 images to the understand what is his preference, and then adapt this pipeline to his tastes. Okay. And in order to do this, of course, a very light pipeline that can be easily adapted without having a large training data set. On the other side, I also think that the design of end-to-end learnable neural-based pipeline will continue to be a nice idea, because it's difficult to have experts that can put their knowledge in all the different steps. And it's also, from a research point of view, it's very interesting to have a black box that can perform end-to-end all the different operations. But this would require a very large parameters, and this will reflect into a very large data set. As you were saying, there is no way that we can actually enable such a data set. And so I think that some unsupervised approaches combined with some aesthetics metrics that could work for any contents could be the next step for that part of research. So actually, let's say, I do not see a single line of research in the future. I see two of them, one going into the current direction of end-to-end learning based, and the other going into very small but very flexible and very adaptive.
Okay, thanks. That's all questions from my side, since during your answer you have answered both of them. Does any colleagues from the... Yes, please.
Hello?
Скажи громче.
Okay, I have a question. How did you optimize the parameters of your approach? Did you use the expert photographer, or you did it based on MOS?
It was actually just the preference of me and my team. So no expert photographers, no expert users, no large base of users, just our preferences.
Okay. Can we optimize this process in future? For example, to adapt your methods from domain to other domain?
Which domains, for example?
From one camera to another camera.
Yeah, that's exactly the point. You can adapt this very easily since you just have less than 20 free parameters. The main idea is to also adapt this to different users, so that now in the picture I see 3 persons. Okay, suppose that you both have the same type of phone. This pipeline could be adapted to your preference of each one of you very easily, with just making you select your preference one on 5 different presets, for example.
Thank you.
Okay, thank you very much. Professor Simone Bianca, thank you.
Yes, thank you again, and thank you for inviting take attendance in our event. Thank you and welcome to our future events, and thank you again.
Thank you. Thank you.